the last half of the talk from yesterday was a little more telegraphic in the transparencies, given the amount of time I thought I would have.
You really just finished 11 yesterday, did you?
No, I didn't. No, no. But I was hoping to spend some time to beef up the transparencies, but we're a little busy trying to figure out what CDMS has seen. So I'll have to make do with the transparencies I had already yesterday, which were not bad. But I'll try to beef up some things on the board, if that's okay.
Is that the expression just for trees or for all?
No, this is for all loops. The conjecture is that this knows about leading singularities to all orders of perturbation theory. All leading singularities to all orders of perturbation theory. And there's a number, I mean, for it to be true, for example, for MHV amplitudes, all this expression gives you, it isn't even an integral, it just gives you one thing, which is the MHV tree amplitude. And so that sounds very surprising, except for the quite non-trivial fact that when you draw those pictures that I was drawing yesterday for what the leading singularities are for MHV amplitudes, you find that they're always proportional to the MHV tree amplitude. And then, so this really makes a prediction that pattern goes on. At any n and k, there is some fixed number of objects that will ever appear in the leading singularities. And the reason, so that sounds like a much bolder conjecture than it is. Well, no, it sounds like a much bolder conjecture before you realize that it's something that's guaranteed to be both conformal and dual conformal invariant. That's the real magic. I mean, it's almost impossible to write down things that are both conformal and dual conformal invariant at the same time. It's the fact that it's managing to do that, and therefore is baking in all of the symmetries of n equals 4 super Yang nulls in one object that makes it now much more reasonable that it's doing that.
So the group theory of this whole generates
Yes.
both is what's known about that? What invariants are there?
That's what our German friends have spent many years exploring. But that's this gigantic Yangian that you get from I don't know. I mean, I myself don't know what that means, but it's what you get from commuting conformal and dual conformal invariants. And there's some gigantic integrable structure that goes with it. That's the same integrable structure that governs the spin chain. It's the same integrable structure that Vieira and Kazakov and Gromov have been exploring. It's the same integrable structure that will eventually completely solve n equals 4 super Yang mills. But that structure is showing up at the level of scattering amplitudes. Now, that people had seen already, and that people had noticed, in fact, that just at the tree amplitudes, the BCFW computation of the recursion relations was making conformal and dual conformal invariants obvious. So at tree level, the correct combination of residues here is giving you the, at least in the obvious way, is giving you the amplitude that's computed in one of the many forms that BCFW would compute it. And then the equivalence between all those forms is guaranteed by all these residue theorems that give you very non-trivial relationships between all these invariants. But somehow this object also knows about all loop information. It knows the piece of all loop information that's completely unambiguous. The leading singularities, the things that are no infrared divergences, perfectly well defined, but most certainly know about loop level information. But just to remind you, that's the original object, and then it was motivated by this picture it was motivated by this geometric picture, which I'll very quickly flash again. It was motivated by this geometric picture for momentum conservation, where you start realizing that momentum conservation in this n-dimensional space is the statement of the orthogonality of two planes. You introduce an auxiliary object, a k-plane, to enforce that constraint as a pair of linear constraints. Now, here you're making a choice, notice, right? I mean, strictly speaking, all I need to do is introduce a 2-plane, even if I wanted to do it this way. So I'm putting in something. I'm making some kind of assumption. I'm putting in something special by saying, no, I insist on doing it with a full k-plane. Okay? I insist on doing it with a full k-plane. And this GLK, this idea that there's really a k-plane here, and not just k vectors, it plays a very important role. This is the new interesting redundancy in this business. It's the replacement for gauge invariance and diff redundancies as one of the engines for allowing things to well, Well, it's the analog in the Grassmannian of the redundancies that we are used to talking about in space-time. I say that because something we're going to see in this talk is that there's a lot of life in the Grassmannian itself, and I'll try to make that more precise as we go along.
So I mean, K ends up being the number of negative helicity states in the amplitude.
That's saying it in a non-supersymmetric way. What it really is the R charge of the. So when you label the external states by these Grassmann parameters, K is any given amplitude has some number of these etas, okay, and it's just it's a total number of etas. It's the R charge. So the amplitude breaks up into a sector which is a sum over different, which has different R charges, and K is just that R charge. Okay. I'm colloquially saying it's the number of negative helicity gluons because that's at component level. There's tons of amplitudes that are related to each other, but the ones with K equals 3 are the ones that would have 3 negative helicity gluons somewhere. Now, there's something I don't really have. There's something. It could be that supersymmetry is not playing it could be that supersymmetry is not playing a particularly critical role in this story. Although in everything, well, let me not say that. Sorry. It would. Well, okay. You see. I'll just spend 2 minutes saying this. One of the things that makes supersymmetry very beautiful from the point of view of scattering amplitudes, and makes supersymmetry even more natural from the point of view of scattering amplitudes than from the point of view of local Lagrangians, is that supersymmetry allows you to put all the multiplets, all the helicities in one multiplet, and unify everything in one multiplet. And it's supersymmetry that explains all these otherwise bizarre relationships between amplitudes with helicities put in different places. Okay, so for example, the 4, the ij to the 4th in the Park-Taylor formula, that 4, that numerator, is a direct consequence of n equals 4. That's in fact, I mean, that's how that's a way that the amplitude is telling you that it wants to be made supersymmetric. Even the non-supersymmetric amplitude is telling you that. In other words, there's lots of relationships between the amplitudes that become manifest by thinking about it as one object, as one supersymmetric object projected in different ways. And now, it turns out that when you take this object and you gauge fix it in this way that I discussed briefly at some point, gauge fix it in this completely canonical way that by setting some k columns of this k by n matrix to 0, it turns out that in this gauge fixing, it's particularly trivial to pick out component amplitudes. And in fact, you can just do the Grassmann integrations trivially. You don't get anything. You get 1 if the particles that you want to assign to negative helicities correspond to the columns that you gauge fix to the orthonormal basis. Okay. Now, any one of these can be thought of as giving is one chart on the Grassmannian. They don't cover the entire Grassmannian. The collection of all of them covered the entire Grassmannian. So we see that even non-supersymmetrically, there is a sense in which there is one universal object, and that the different component amplitudes are different projections of the same object. It's the same object integrated over different charts on the Grassmannian. So there's some sense in which all the amplitudes are unified, even without supersymmetry. What supersymmetry allows you to do is like a convenient trick, is sticking in one chart to learn what the answer for the integral over any other chart is. But there is some other thing here which is allowing you to unify all the even non-supersymmetric objects together. So that's a very weak suggestion that perhaps there's some version of these ideas that does not critically rely on supersymmetry. But I don't want to spend too much more time on that. Yes?
You needed the supersymmetry so that you could mod out by GLK instead of SO?
Right. So somehow, so from the entire geometric logic, I really need supersymmetry. But I'm saying from the point of view of the final concrete answer, there is some integral with a universal object, and if you take that integral and integrate it over different charts on the Grassmannian, you'll get this helicity configuration, that helicity configuration, that helicity configuration, and so on. So it's now in a gauge fixed form. So you're not going to. I mean, it's a gauge symmetry, so it's not really there ever. Okay. So how you would have guessed that form, I don't know, without the supersymmetric motivation. So that's why this is a very weak motivation, and perhaps it isn't correct. Okay, but again, and this was the really important point, which I didn't really explain, but it's a really trivial piece of linear algebra that once you determine that you want to do this integral over k-planes that contain the lambda plane, an orthogonal to the lambda tilde plane, and you just manually demand that you're only integrating over the pieces of this k-plane that are orthogonal to the lambda plane, and you do a change of variables in order to map the k by k determinants, the k minus 2 by k minus 2 determinants, you discover momentum Twistor space, and the fact that the formula, stripping off the overall supersymmetric ordinary momentum and supermomentum conservation out in front, has precisely the same form as the old formula, with k replaced by k minus 2, and the ordinary dual twistors replaced by the momentum twistors. Okay? So, in fact, there's a very interesting chain of dualities here. So you could then imagine doing it again, and then going to the dual space of this guy, and continue lowering k. This says, roughly speaking, every amplitude is the MHV amplitude, but after a crazy chain of dualities, a very, very crazy chain of dualities. In other words, this formula is not only interesting because it exhibits manifest dual superconformal invariance. On top of that, there's the remarkable fact that the structure is exactly the same as the original integral, precisely the same as the original integral after you factor out this piece.
Do it once more?
If you do it once more, you see, this is a momentum space formula, really. There's no Fourier transforms involved in using momentum twistor variables. It's just a completely algebraic. It's algebraically using the incidence relations. To go to the ordinary twistor space involves a Fourier transform. So you could take this formula and decide that you wanted to go to its coordinate space. If you went to its coordinate space, you would get a formula that's then, well, is exactly the same as the right.
Going from usually.
I'm really not saying much more than that. No, you don't. Doing it twice, you don't get back to the same place. You get to something else. And the reason, by the way, is that all of these delta functions become more and more scrambled. So that's what I'm saying. It's that if you do it twice, you don't come back to the same place. You just keep going to. Right, so this is the fermionic T-duality, which is I don't understand too well myself, and there is something, I'm told there's something funny about it, so that it's not inconsistent with this idea that you do it twice and it doesn't come back to the same place. But definitely, you do this twice, you do not come back to the same place.
So if you keep doing this, you keep removing two rows at a time.
Right.
You get to either 0 or 1 row.
You can get to 0 or 2, or odd or even, but that's right. Yeah. So that's what I was saying. If k is even, you can, in principle, in a sense, reduce all amplitudes to MHV amplitudes in some suitably dualized space. But I don't want to make too big a deal of this because all the action is happening in very, very singular support on what happens to these delta functions. As you really, what I wanted to say is that it's not merely that the theory is dually conformal invariant, which is already remarkable. It's that the structure is just identical, is exactly the same in the ordinary and the dual space. Okay. So and as I said,
the T-duality that as it was, they do conformal invariance. It's the same, but you've lost sort of two of this.
Right, that's right. So and again, in the entire story in ADS 5, exactly what's going on with the fermions is not very, very clear yet. And the entire story is what's going on here with the fermions. Right.
Nima, aren't you just saying that this is recursive?
It's recursive, yeah, but it doesn't come back to the same place.
No, but
yeah.
This is in some sense what BCFW tells you.
No, it has nothing to do with BCFW at all. This is really something exponentially more interesting than that, because it's not just that. Again.
So what happens if you start with k equals 3?
Yeah.
This takes you down to k equals 1, which can't be satisfied.
Right. So again, all the action is going in the fact that as you go from one space to another, those delta functions out in front are doing. I mean, the information is contained in very singular support.
So you get 0 times infinity.
Yeah, that's right. I mean, so I presume I haven't actually done it. This is a theme. I don't know very much about, but I mean, we haven't explored it very much, but I'll just say that it's extremely likely that scattering amplitudes have a huge amount of information localized on places we normally don't look. Localized on very funny delta function localized places in momentum space where we normally don't look, but there's an enormous amount of information there. One hint along these lines, for example, is that things that are smooth in Twistor space Fourier transform to things that are singular in momentum space, and vice versa. Things that are singular in Twistor space Fourier transform to things that only have a single momentum conserving delta function. So by focusing on things in momentum space that are just happen for generic momenta, we could be missing things. A lot of this information is buried in things that are supported with funny collinear singularities that we normally just throw out for generic momenta in momentum space. Okay, but I just wanted to emphasize, as I was saying yesterday, that each individual residue of this object is something interesting. Each individual residue is a Yangian invariant. All the relations between them are presumably encoded by the very non-trivial residue theorems that are guaranteed by the global residue theorem, and generalizations of the global residue theorem that we don't quite know yet, but which must exist, that involve not just the simple residues, but the composite residues that I briefly alluded to yesterday. Oh, I did. Yeah. So the global residue theorem is the following statement. So first, a local residue is the following. So this is what I defined yesterday, but a local residue is if you have a function of n complex variables, you find n polynomial factors in the denominator, you go to the place where they vanish, and it's just the numerator divided by the Jacobian of the polynomials in the denominator. The global residue theorem just tells you that if you choose a way of decomposing the function in this way with these polynomials once and for all, okay, so you've made this choice. This defines some zero set of these guys, defines a whole bunch of residues, that as long as the numerator doesn't blow up too quickly at infinity, that the sum of all of these residues is equal to 0. Okay? And this is if all these things are linear factors in the z's, you can prove this by doing Cauchy's theorem one at a time. But this is not something you can in general prove by doing Cauchy's theorem one at a time. And but it is a true theorem.
Why do you do that if the a's are polynomials and the z's?
Because if there's something that's quadratic in one of them, then if you just dumbly do the Cauchy theorem in one of them, now you have something with square roots all over the place. It's not even holomorphic anymore. Okay, so instead, what you do is you find some mapping, some canonical mapping between this complex function and some real function, and there's many funny things about this residue which are different than one complex variable. In no sense does the contour enclose the pole here, for example. Okay, it's just some. It's like many S1s, but there's in no sense does it enclose the pole. That's related to the fact that it has this funny alternating property. Okay, this residue is really a map. It's really a map from given, and this is going to be a theme that's going to come back. And you'll see how important this way of thinking is in a moment. But it's really a map. Given some numerator and a denominator, it's really a map that takes these things and returns a number out of them. It's some alternating map that has that property. You'll see why it's well, like I said, you'll see why thinking that way is important in a second. Oh, I forget why I was talking about that. Sorry?
David asked a question about what the global residue.
Oh, sorry. Yes. So that's the global residue.
Can I ask a question about where you were about to get to yesterday, which was this thing about the particles?
Yeah, that's exactly what I'm getting to now. This was just supposed to be a review of yesterday, but I just want to say that there's a huge amount that's interesting to understand about the residues themselves. But I want to talk about something which is I think even more interesting and important here, which is the way in which they're put together and why it is that the way in which they're put together allows something that has a local spacetime description to come out. And so the best way to do it is to start with some examples. Okay, so these are what the NMHV tree amplitudes look like. In fact, I claim this is the nicest way of writing down what they are. You don't have to write down the explicit expressions. Really, the nicest way of writing down what they are is thought of as the following residues of this object. The reason this is the nicest way of writing them down is that all the relations between them are manifest. And if you wanted to go compute them in the end, they're there, sitting there once and for all. Okay. I told you that you can compute things using BCFW or its parity conjugate, and this is what the contour ends up being for its 6 points. Now, how do we know this? At the moment, we're just noticing, right? This is just the pattern. So you notice this pattern, and now I'm going to explain where this pattern is coming from and why it had to be this way. But just so you see what the pattern is ahead of time, so you take the residue where the minor 1, so this notation is when I say the minor 1, this really denotes 1, 2, 3. So we always have these cyclic minors. It's a thing that denotes 1, 2, 3. Sometimes I might write down something like that. We might, and we will have occasion later in the talk to talk about non-consecutive minors made out of non-consecutive columns. And when that happens, I'll just write them all down. But when you only see one of them, it's unambiguous, and it refers to the first one of the chain.
But when you say 1, 2, 3 like that, isn't that only for k equals 3?
So this is all k equals 3. That's NMHV.
Oh,
okay. So
everything is k equals 3.
So for a lot of what I'm talking about, I'm just talking about k equals 3 because this is the first non-trivial example. So it's 1 plus 3 plus 5. This parity conjugate form is negative 2 plus 4 plus 6. The 7-particle form is this form 1, 2, 1, 4, 1, 6, 3, 4, 3, 6, 5, 6. You see, it's odd, even, odd, even, odd, even, just always written in increasing order with n minus 5 terms. And just flipping even and odd on the other side. Okay, so that's a relatively nice looking contour. Now, the fact that these, so this is it in general. The fact that these two are actually equal to each other is very non-trivial, and is a consequence of the global residue theorem. Okay. The way of proving it is actually, we developed some techniques in our paper for how to prove this. It's actually not, if you try to do it using literally the global residue theorem one step at a time, it takes many, many chains in order to prove this. So we actually, but there's a way of thinking about this as in terms of certain kinds of gauge invariants that test whether two contours can be deformed into each other. And then you compute this invariant object on the contour on one side and the other side, and you show that they're equal. Of course, case by case, you can also find manually the global residue theorem that converts one to the other. But that's why I said yesterday, it's a homology argument. These contours are in the same homology class. Okay. This is some other notation. I probably won't use this so much in the talk, but we find it useful. You have to set n minus 5 minors to 0. When n starts getting big, it's more convenient to talk about the minors that you're not setting to 0. And so the open circles here just denote the minors that you're not setting to 0. Okay, so there's this amusing pattern for the minors that you're not setting to 0. Okay, so, and you sum over all of those guys. That's the BCF form, and the parity conjugate form just flips it. Now this is where I got to yesterday. So we're going to see that we can do two things, two very natural things from the point, and when I say natural, sort of mathematically natural from the point of view of the object itself. There are two things that just looking at it further, it asks you to do. One of them involves taking each one of these residues and breaking them up even further. So they're already pretty discrete things. I'm summing all these funny discrete things. One natural operation is breaking it apart even further. Okay? And we're going to break it apart into lots of component pieces. And we'll see for any given residue, the component pieces, some of the component pieces, remember I told you each one of these residues each one has spurious poles, each one has some nice poles and some crappy spurious poles. Right? This process of blowing them apart further is going to break them up into objects, some of which are just beautifully local objects all by themselves, and some of which are not. And what we'll find is what's special about this contour is that all the ones that are not cancel in pairs. You're just left with the ones that do. And furthermore, the ones that do give you a representation of the amplitude, which is precisely what you get from the space-time Lagrangian and light cone gauge. So how could we have discovered the Lagrangian? There's no way in heck we're going to get to negative a quarter f mu nu squared. That doesn't make any sense. That's built in the space-time gauge redundancy, right? We don't see the space-time gauge redundancy at all on this side. The only way we're ever going to do it is to match some very physical gauge in space-time. It always made sense that it had to be light cone gauge, and that's exactly what's going to happen. In fact, it's a souped-up version of light cone gauge. The souped-up version of light cone gauge that gives you the so-called MHV Lagrangian expansion, or the CSW rules. So this is going to show a contour deformation, if you like, that takes you from BCFW to CSW. But in doing that, it makes completely manifest the space-time Lagrangian. Okay? So so one natural step is going to blow up the residues further, and will make the space-time will make space-time manifest.
What do the two words "blow up" mean?
Well, it's not meant to be a fancy word. It's literally we're just going to take any given residue and break it up into the sum of a whole bunch of pieces in a very natural way.
Oh, okay.
But something which is even more surprising to me is that there's an equally natural thing that you could want to do, which is to sew the residues further together. See, the residues as I define them are each local residues. But the way I describe them, I cannot give you one global function such that every term in the contour that I defined, I'm using the word contour sloppily. By contour, what I meant as a physicist is the sum of the following local residues. But as a mathematician, if I said the word contour, I would have to specify one function for you and have all of those zeros be the zero set of that function. And there's no way you can do that. Naively, there's no way you can do that. So you might just be bothered by the fact that we're adding things together that don't seem to come from one function, that we have to add up lots of different functions. So you might just be motivated to find a unique function, the sum of the zero sets of which give me the contour. Okay? Trying to give me the sum of the residues that I defined. We'll find that you can do that, and that doing that actually has a very natural physical interpretation. That trying to do this thing that's very natural mathematically leads to something with a very natural physical interpretation. It's a physical interpretation of literally adding one particle at a time. You take the 5-particle amplitude, and there's literally an operation that you can do to add the 6th particle, add the 7th particle, add the 8th particle, such that if you then took the soft limit of this 8th particle that you added, it's guaranteed to have the correct. It's guaranteed to have this correct soft limit. It matched to the 7-particle amplitude and the 6 and the 5. In other words, there should have been something natural. It's funny to have the physics depend just on this. If you have 1,000 particles, to just have it depend on the space of 1,000 planes, the space of k-planes in 1,000 dimensions. There should be some way of gluing these things together, relating different ends to each other in a natural way. But each one of these contours is a funny, discrete thing, and they seem to change in a very discrete way as you go from one to the other. That turns out not to be the case. That what's special about this contour is it allows a unification, a gluing together into an object that has a particle interpretation, not in the space-time, but purely internally within the Grassmannian. And that particle interpretation is what ends up allowing a deformation of this object into something that turns exactly into the Twistor string theory. And I'm going to make an analogy at the end that this theory is like the quarks, and the Twistor string theory is giving you the hadrons. But there's really there's a flow that takes you from one to the other. The flow that deforms the function and takes you from one to the other. But this formulation is the one where all of the symmetries are manifest, okay? and all the structures are manifest. So that's what I'm going to tell you about.
Just a question.
Yeah.
The old Twistor string, I thought the conclusion was that was actually equivalent to some conformal supergravity.
Right. Well, everything
doesn't preserve.
Yeah. So everything I'm talking about here and now is only about tree level. Okay. And so that's I think one of the pieces of good news here. Okay, is that we know that the object we're talking about knows correctly about the loop amplitude. I don't know how to get the polylogs and the infrared divergences and everything, but it definitely knows about 17 loop amplitudes with all the correct cuts and everything, right? So I think there's some hope now that perhaps we can, either the Twistor string is being incorrectly interpreted, or it's not really a string theory, or it's or something. But really what I want to show you is that every natural mathematical thing that you'd want to do with this object does something important physical, and brings together, as I said before, every idea but the Wilson loop in this business. Yes?
Why is it restricted to tree?
So for example, in this entire discussion, this is a contour that picks out the tree amplitudes. If I go to 8 particles, for example, some other residues correspond to a 2-loop leading singularity. Okay? So in general, I'm picking out a tiny subset of all the residues
Leading singularity in the 8 particles.
in the 8 particle amplitude. Okay?
What about the 2 loops in the 7 particles?
For the 2 loops in the 7 particles have this funny property that we already saw for MHV, that all the 2-loop leading singularities are in fact exactly given by objects that occur already at 1 loop, so they're exhausted quickly. Okay,
Nima, you're saying
yes.
that if I don't put that particular combination,
Yes.
some other combination,
Right.
it would give you the leading singularity.
So, in fact, I mean, this is part of the sort of classic story of where BCFW recursion relations came from. Each term in the BCF recursion relation is itself a leading singularity. It's a 1-loop leading singularity. Okay, but there's no contradiction. All of these things are leading singularities. But it's just that what gives you the tree amplitudes is a linear combination of certain 1-loop leading singularities that are associated with cutting 1-loop diagrams open. But there's also all-loop leading singularities as well.
But even, let's take MHV.
Yeah.
Where we have presumably a formula for the
Right. So it's,
is that not that formula, the exponential formula, naturally come out of it?
no, that's the object that we're not making any contact with right now. Okay, so that's what I'm saying. You take the MHV amplitude. All this formula gives you is the MHV amplitude, and
all of its you are making contact with all of its.
I'm making contact with all of its leading singularities, which happen to be the MHV tree amplitude. So we're making a prediction that's incredibly falsifiable, right? If someone discovers that some way of putting together MHV amplitudes together is not proportional to the MHV tree amplitude, we're just wrong. But I just think there's no way that it's true, and it's known that all the leading singularities of this object are the tree amplitude up to 3 loops and 5 particles or whatever people have checked. At 2 loops up to 6 particles, at 3 loops up to 5.
But it doesn't work.
No, sorry. We're talking about you're talking about something else. You're talking about the BDS conjecture, and I mean, but it contains them, but whether or not the specific form of the BDS conjecture is true or not isn't germane to what the remember the leading singularities are even though they know about the loop diagram, they're completely computed by gluing tree amplitudes together. You don't actually have to compute a loop amplitude. You don't actually have to compute a loop amplitude to check a leading singularity. You just have to draw these complicated pictures. Right.
We could expect a loop amplitude.
Oh, you could try to do that. That's right. You could, and so.
My question was, do you get? I mean, it's
Are you asking whether the leading singularity method is known to work at 6 particles for 3 loops? I don't think it's known to work at 6 particles for 3 loops.
I was asking whether even in the case of, say, the 4-point function, MHV, you can get, you have some way of getting the coefficients that allow you to build up the exponential.
Not from this object in any obvious way right now. In fact, maybe I'll say some things about that at the end. But really, so that object is the Wilson loop. That object is that's what I meant. I mean, it's the polygonal Wilson. It's a light-like Wilson loop in the dual space. Somehow, it's for MHV amplitudes. It's true that you take the tree amplitude and you just multiply by that object, and that appears to be the entire amplitude. So there seems to be some simple way of combining the Yangian invariant. In that case, it's just the MHV tree amplitude with this object that has all the ugly infrared divergences and all that stuff in it to get the physical answer. So perhaps there's some way of melding these things together at all orders. And if I have time, I'll say very few things about that. But that's I think the next and perhaps the last thing to figure out in this business is how to combine these two threads together. But the rest of this talk is really just back to tree level. Okay, so just back to tree level, but already there has to be some miracle happening. I mean, somehow we have to go from this extremely combinatorial even odd to something that looks like Yang-Mills theory in spacetime. Okay, so that's what I want to expose, and the analog of that purely internally within the Grassmannian. So in order to do that, let me just give you a lightning review of CSW. So the CSW rules were inspired by the disconnected prescription for Twistor string theory, but never really derived in that way. That they were inspired. But what you can think of them as really like a Lagrangian. Like someone hands you a Lagrangian, but the vertices of the Lagrangian are MHV amplitudes. They're not MHV amplitudes. They're MHV vertices, and what they are is some off-shell continuation of the MHV amplitude. So one of the legs here is off-shell. So when you go to compute the MHV amplitude associated, but the rule associated with that vertex, you use the MHV amplitude and you pretend that even though this guy is massive, that there's a spinner associated with it, lambda p, which is the momentum flowing through that, times some auxiliary spinner. Okay? So the CSW rules are not manifestly Lorentz invariant. Okay? And that was quickly understood as being due to the fact that this is really light cone gauge. So what you do is simply the following. You go to light cone gauge. Now in light cone gauge, you only have the physical helicities, so you have plus, plus, minus, 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 plus interactions, and plus, plus, minus, minus. And what you can do is do a change of variable to eliminate the plus, plus, minus vertices. So if you do that, you must induce an infinite set of MHV vertices to make up for the fact that it's now impossible for you to get to the MHV amplitude. Okay? So you do this change of variables and you induce this infinite set of vertices that give you all MHV vertices, and now you have a Lagrangian. Of course, in light cone gauge, it has some non-locality in the light cone direction, but that's fine. But it's perfectly local in all the other directions, and so that's it. And you start computing with that, and that gives you a very efficient way of getting the diagrammatic calculations. So it's extremely nice, but you should think of it as a souped-up version of light cone gauge. Okay, so it's as succinctly as possible encoding the local space-time physics. Okay? Now, these pictures are associated with with certain kinds of localization in Twistor space. I don't have a lot of time to review this, but one of the stories that Ed started with was the observation that MHV amplitudes can be thought of as being localized on lines in Twistor space. And so if you're putting together MHV amplitudes, then there's a line corresponding to one of them, a line corresponding to the other, and the lines intersect. Okay? The intersecting of the lines is telling you about the existence of the propagator. Really, if you like, when we draw these pictures, the intermediate point is that point that I'm not labeling in this picture. So the lines intersect. Okay? And so what you do, since there's color ordering, you can draw all the MHV. You can just draw all MHV diagrams. And in fact, this picture with the intersecting lines is another convenient way of mnemonic for the Feynman diagrams. For the Feynman diagrams, you just sprinkle 1, 2, 3, 4, 5, 6 on 2 intersecting lines in every way that you can, maintaining cyclicity. Okay? So there's a total of 9 CSW diagrams for this 6-particle amplitude. 3 of them which have 3 points on one line and 3 points on the other, and 6 of them that have 4 on one, and any 2 are on the other. Okay? Okay. Now, I told you one way of deriving the CSW rules by going to light cone gauge and doing a field-view definition. There you have to be a little bit clever to find that field-view definition. There's another way of getting to the CSW rules that I want to mention, which is much more in line with all the other sorts of developments in the scattering amplitude business, which involves some kind of deformation on the external momenta. So there's the famous BCFW deformation of momenta, where you pick 2 particles and you deform the lambda of one of them and the lambda tilde of the other to conserve momentum. Well, there's something else that you can do that Rissager used, which is even simpler in many ways. He said, take all the negative helicity particles. It's simplest to say in a non-supersymmetric way, so I'll do that. Take all the negative helicity particles and just deform their lambda tildes. Okay? By some parameter alpha I, z, and now some auxiliary spinner zeta tilde. For momentum to be conserved, these have to satisfy a constraint like that. Okay? And so the Rissager deformation, if you have k negative helicity gluons, is labeled by k minus 2 parameters, imposing that constraint. Okay? So there's a k minus 2 parameter deformation of the lambda tildes that you can talk about. Now, it's easy to show that under this deformation, the amplitude vanishes at infinity. Cauchy's theorem allows you to break up the amplitude as a sum of lower point amplitudes glued together. The logic is identical to BCFW. And so this gives you a new kind of recursion relation, called the Rissager recursion relations. And Rissager showed that this, in fact, gives you CSW. That you do this once, and then you do it on each blob again and again and again, and recursively this, in fact, leads to CSW. So this is another derivation of CSW. I mention this because what we're going to get from our simplest deformation is actually going to give us both things. Okay, so let's see how this is going to happen. So let's go back to our object. This time, I'm just writing it down for the NMHV case, although you can do this in the completely general case as well. I'm just, for simplicity, writing it down in the NMHV case. I told you that, that our object, if I use these momentum twistor variables, which are very convenient because they strip off the overall momentum conserving delta function, so I don't have to worry about it. So that's all contained in this factor. And then, remember, it was an integral over k minus 2 planes. K was 3, so this is the simplest possible thing. It's like dd1 over d1 up to ddn over dn, and this delta 4/4 that contains the sum of all these d's with the momentum twistors. Now, from the very start, in any one of the forms of this formula, you might have complained that it's really funny to have a contour integral that has delta functions in it. This is really stupid to have these delta functions. And in fact, these were never really legal delta functions. It's always something that, it's something we said, but they're not delta functions in the sense that when you change variables, you don't pick up modulus signs in the Jacobian. They're always holomorphic delta functions. It doesn't, so where when you do a change of variable, you don't pick up the modulus sign under the change of variable. That means what they really were all along was poles. Okay? They're really poles. They're just poles that we're enforcing. Okay? So if you see delta of x, I can holomorphically think of it as 1 over z, but I'm enforcing the pole that z equals 0, in the sense that if I integrate anything against it, then I'm specifying the contour to force z equals 0. And part of the reason we wrote these things as delta functions to begin with was a little historical. We were a little scared of these multidimensional contour integrals, and we were trying, even though we were being forced to talk about them, we're a little schizophrenic in our attitude about having all these complex variables and all these poles all over the place. Well, they're just there. Every one of these things is actually an honest pole. Okay?
So instead of a delta function, you really have a bigger integration.
Yeah, no. I mean, the integration is there. I mean, we're integrating over all these things anyway. Just we had some of these delta functions. What we mean by delta function. So what we mean is literally this. So here's a simple example, right? So I take this guy, and it really breaks up into two bosonic delta squareds and a fermionic delta 4. Sorry, that should have been a delta 4. Anyway, the fermionic one is fine. It's just a polynomial. But these bosonic ones, really what they are is, well, I mean, if I have delta of x, I mean, this is totally trivial. I mean, there's no... There's nothing deep about it, but you can see the small hesitation for why we didn't want to write it this way. Delta squared of x, well, this would be 1 over x0, x1. Okay.
Over x.
Well, delta of x I can replace holomorphically by 1 over x. Okay. In the sense that integral dx delta of x f of x, I can think of instead as the integral of 1 over z f of z, where I enforce the contour around z equals 0. That's all we mean by it. Okay? But what's funny is when you have things with Lorentz indices, this thing doesn't look very Lorentz invariant. Of course, course, really, neither does delta squared of x looks Lorentz invariant. It's really delta of x0, delta of x1. It's just that on the support of the delta function, it is Lorentz invariant. Okay? So you just have to bite the bullet and say, okay, if I want to write it as a pole, I really do have to introduce I have to expand. Let me shrink this size so you guys can see what I'm doing. If I want to write it as a pole, I really have to expand the argument. I have to pick a basis of spinors, in this case, 2 of them, chi and zeta. I expand it in that basis, and this is really what I have. So really what I mean by this is there's some chi zeta, the delta of this guy dotted into one of them, the delta of that guy dotted into another. And really by those deltas, I mean poles. They're really just poles, 1 over that object. So it doesn't look manifestly Lorentz invariant. It is Lorentz invariant on the support of the poles. Okay? So that's perfectly fine. But when you do that, of course, immediately a thought occurs to you. Why not deform the contour? Just take it and just take one of them. And just to get going, let's just take one of them and deform the contour off one of these delta functions and push them on everybody else. So what is that going to do? That's going to take this nice, beautifully Lorentz invariant residue that we have and is going to express it as a sum of a whole bunch of non-Lorentz invariant objects. What could that possibly be? Well, let's see what it could be. Okay? In this simplest possible case, each one of these guys corresponded to one of the minors. When I take the pole and I deform it off of one of them, then as I push it back in here, I'm going to set, if I talk about any one of our residues, we're already setting one of these guys to 0. But having deformed the pole off the other guy, I'm going to set one of the other ones to 0. Okay, so I'm going to take any given residue and express it as a sum of 5 terms. Okay? Of 5 terms where in those terms I'm just denoting here, the other guy that's being set to 0. Okay? Every one of those D's is actually one of these minors. Okay?
dA that was set to 0 previously.
Yeah, so for example, in talking about minor, so what I'm doing is now saying what happens when you take residue 1, and you take residue 1 and you now use Cauchy's theorem to express residue 1 as a sum of 5 terms. Right.
In the original turnout was setting dA, going to dA equals 0.
Right.
And dA appears in the measure in the denominator.
Sorry. Yeah. So what I was doing, I was also setting one of these guys to a pole. Okay. So in other words, beforehand I had this multidimensional integral, and what I really meant by these delta functions is I was just forcing a bunch of those guys to be on their pole, and then I was forcing some of the poles on the other guys. No, it's not. I mean, there's many variables. So they aren't double poles. I can show you in more detail, but they're not double poles. Okay. Now, of course, you actually have to do the computation to see what the residues are. But without doing any work, you can see what kind of localization properties they have. That's because every one of these pictures, every one of these minors is associated with a very simple picture in CP2. Okay, so for example, the minor 1, 2, 3. If 1, 2, 3 vanishes and 2, 3, 4 vanishes, that means that 1, 2, 3, and 4 are all on a line. There they are. Okay? So this thing has a localization in CP2 that looks like that. That's a legal CSW diagram. When you compute the residue, it's exactly what you get from CSW. Okay. But this one is not. 1, 3 has 1, 2, 3 on a line, and 3, 4, 5 on a line. Well, 6 isn't anywhere. I shouldn't even drawn it there. Sorry, I did that totally wrong. 6 is just some random spot here. Okay? And I also screwed it up here as well, I'm sorry. But anyway, this is not a legal CSW diagram. This thing is a legal CSW diagram. That one isn't, and that one is. So this individual residue has now been blown up into 5 terms. 3 of these terms look like they're localized intersecting lines in Twistor space, and therefore have directly a local spacetime interpretation. 2 of them do not. Okay. But that's not the full contour. The full contour is 1 plus 3 plus 5. These guys all appear in 1 plus 3 plus 5 in opposite orientations, and the antisymmetry kills all of them. They cancel in pairs. And what you get from the remaining ones is every one of the 9 CSW diagrams. Notice there's 3 good ones and 2 bad ones. All the bad ones cancel in pairs, and so there's 3 from 1, 3 from 3, and 3 from 5. That's 9 CSW diagrams, that's all the CSW diagrams. Okay? So this incredibly natural operation, you have these delta functions, they're really poles. The first thing you do is deform the contour off the pole just to see what happens. You do that with the NMHV amplitude, you discover space-time. You discover space-time in the sense that on this contour, you see something that comes from the Yang-Mills Lagrangian in light cone gauge.
What you're saying is those delta functions are really a prescription.
They're really all poles, right? They're really all.
Your contours are really defined.
Exactly. In other words, right.
Yeah.
Right.
But only a subset.
Oh, right.
It's 2 out of.
That's right. You know, a way of, so somehow in the original geometric picture, it's saying we have these K-planes that contain the lambda plane, orthogonal to lambda tilde plane. It's saying, okay, they don't have to be completely orthogonal to the lambda tilde plane. You can relax that a little bit. Okay, and you're just deforming it off a little bit. But the original delta functions from that picture were demanding that it completely contained the lambda plane.
You should just
relax all of them. It probably does. It probably does. And in fact, what I'm about to show you really suggests that you probably should. And but again, seeing what all these pictures. So
saying relaxing all of them can't be done in the Lorentz invariant way.
That's fine. But we see it's right. Oh no! If you want a manifestly Lorentz invariant, no, it cannot be done in a manifestly Lorentz invariant. Right.
All of them have this thing.
Right.
And
which isn't obviously Lorentz invariant, right?
Plus the prescription that these K of these.
Yes, right. That's right. So if you do that, that makes it manifestly Lorentz invariant.
If you remove those K contour prescriptions, you get something, other things.
That's right.
What other things do you know?
No.
Those are anything interesting?
Don't know. In fact, if you go all the way, you'll have even things that don't conserve momentum. So I don't know what it means. It's very likely interesting, but I don't know what it means yet. In fact, you can see that this even odd, this funny combinatorial rule is in fact just born to do exactly this. It's born so that each one of the residues, as you saw, each one of the residues in the general case blows up in exactly this way. A subset of them are legal, the rest of them are illegal, and on the even odd, this funny combinatorial structure, it's guaranteed that all the bad ones go away and the good ones remain. In a sense, you remember there was that identity with the spurious poles and it had to be true and so on, right? And I told you it was very hard to prove that identity in general. This is some very smart way of doing partial fractions on that identity and splitting up the pieces that are spurious. It also is the answer to Eva's question, which is that we are putting in a sense, from the space-time point of view, lots of redundant things, right? What did we buy? What do we buy writing it in this 1 + 3 + 5 form? This is the form where every symmetry of this object is manifest. It's conformal, it's dual conformal, all of the symmetries are manifest. What's not manifest is it comes from space-time. You take it to space-time, and you're losing information in doing that. There are all these things that are canceling in pairs. If you want to see that it can be reassembled into this object that has conformal and dual conformal invariants, you would have to be smart enough to know to add and subtract all these things that were canceling in pairs for where it came from. Okay.
So as you do sort of arbitrary diagrams, are you going to be adding and subtracting infinite numbers of things, or how does it?
At least for NMHV amplitude, they're always cancel in pairs. All the cancellations always happen in pairs.
They happen in pairs, but are you adding?
Right, it's that contour, even odd, even odd, even odd, and all the bad ones cancel in pairs, and the ones that are left sum up cyclically all the CSW diagrams.
It's kind of like you have a ghost where you.
Yeah, it's kind of like that. Okay, now, that was for NMHV amplitudes. What about for general tree amplitudes? Well, for general tree amplitudes, for general K. For general K, we have higher than our minors are 4x4, 5x5, and so on. So we don't have a picture of lines. They're planes or higher things. And so deforming just one of these guys was never going to directly land us on CSW. Okay? And yet it should mean something. Well, what we found it means is, in fact, in the general case, it lands you directly on the Risager deformation. Okay? This is quite non-trivial because you take this object, you do this deformation, you get a sum of a bunch of terms, and you have to recognize the terms as coming from a particular deformation, a particular Rasager deformation. Because remember, the Rasager deformation was parameterized by k-2 things. Okay? But the reason it's all okay, and in fact another a non-trivial thing that sort of guaranteed this had to work, is that there are precisely also k-2 degrees of, we also have k-2 degrees of freedom because of the GL k-2 gauge symmetry that this object has. So the k-2 degrees of freedom in the Rasager deformation match precisely to the k-2 gauge degrees of freedom that we had in this object. So this simple natural act, do it one at a time, just remove one, just deform the contour once, gives you the engine that you can recursively use to blow all the residues apart into things that eventually that have a CSW interpretation and therefore build a space-time Lagrangian. All right. So part 2 is sewing the residues into a contour. So here we're taking the opposite attitude. Can I take this even odd thing, and can I think of that as literally being an actual contour integral, in the sense of being an integral over a numerator and a denominator where I add over some subset of the zero set of this function f. One function f, and I take some subset of the zeros of f, and I add them all up. That's the official definition of a contour. What we defined as residues are local residues. I mean, we had this universal object with all these minors, but then we just locally go in the neighborhood of any one place vanishing and the other place vanishing. It's the question you're asking about, Gary. What about the signs? Right? You know, is it the signs are, the sign is arbitrary here, it's arbitrary there. There's something quite non-trivial about the ability to put many of them together as one object, right? So can they be glued together as the zero set of a single object? In fact, naively, they can't. Naively, they can't. Well, in simple cases, they can. Like in the 6-particle amplitude, we just have a function of a single complex variable. So then it's obvious. So we have something that looks like 1 over 1, 2, 3, 2, 3, 4, all the way up to 6, 1, 2. Okay? But it's just a function of a single complex variable. You just say f is that denominator and you're done. Okay? For the 7-particle amplitude, now we have 6 terms, and it turns out there's some clever choice, there's some clever way of taking this guy and dividing it into product of one function times another function. When I say a single function, I really mean here the product of n minus 5 factors. Okay? I need n minus 5 factors to legally define a contour. Okay? Well, for the 7-particle amplitude, there turns out to be a clever way of breaking it up into the product of 2 pieces so that the entire tree amplitude is contained in the zero set of that. But already at 8 particles, it's impossible. Okay? Already at 8 particles, it appears like you can't just take this and do that. The resolution to this little puzzle ends up being, kind of somewhat remarkable, and takes extremely seriously. And this was really Grothendieck's insight into how to think about these residues. It takes it very, very seriously that you think of them as a map. You think of them as a map with a numerator and a denominator, and it's a map from that returns a number. So let me be more specific. What we're going to find is that. Oh, sorry. What we're going to find is that it's possible. It is possible, it will be possible to write, so there's n minus 5 of these guys, so really I should write it as f. It is possible to write an expression like this that is actually numerically equal to, I mean, it's literally equal to 1 over 1, 2, 3, up to, 1, 2, up to k. Well, I'm just doing the animatree amplitudes for now, but it's true for all k. Okay, it's literally equal to that. But these guys tell you they don't care that it literally looks like that. You have to give me a numerator and a denominator. That means that I can have extra factors here in the denominator, extra factors here in the numerator. You might, as a physicist, be just tempted to just cancel them. Okay? But you're not supposed to do that. You're supposed to just exactly the same factor. You just multiply by a bunch of extra things in the numerator and the denominator. Okay? So it looks like you just cancel them. Okay?
What did you start with?
So what I'm doing is saying, naively, I cannot take this object, the object that we start with. And in general, I can't take this object and split it into the product of n minus 5 things, the zero set of which contains the tree contour. I cannot do that. For k equals 3. It's going to generalize for all k. I'm starting with what seems like a formal mathematical problem in order to show that the solution to this formal mathematical problem has a very beautiful physical interpretation. Okay? But it turns out that you can do something the way the mathematicians would tell you to do it, which is to say, no, you're not allowed to just multiply and divide things. The denominator is a map. The denominator, you have to give me these n minus 5 polynomial functions once and for all. Then you give me anything you want in the numerator, and then I take the denominator and the numerator and I return a number. Okay? So I'm going to get, so concretely what this means is that we're going to have, this is going to be expressible as h of tau over f1 of tau over f minus n minus 5 of tau. So if I just write, so there is some h of tau, some polynomials here and there made out of minors, such that this is going to be true. Okay? But when I define the residues globally, okay, I have to take the zero set of these guys. Okay? To take the zero set of these guys and use them to define the residues. Now, very naively, you'd say if all I'm doing is multiplying and dividing by things in the numerator, then okay, those residues are going to be 0. But they're not 0. That's just too naive. They're just not 0, and you get and in fact, this is the correct way of putting together. No, there really are residues. I mean, it's really like the sort of situation where you have, I mean, a toy example of this is something like that. Okay, and so here you naively think that you can cancel those things out, but you just have to tell me ahead of but these guys would tell you that you have to specify ahead of time that you're looking at the zero set of these guys and then evaluating the zero there. Okay, and of course if you do it in this simple case, you get This will be much clearer when you see the explicit examples. But let me just say that this is formally what's going on, and it'll be much clearer when you see the explicit examples. Yes, this is an explicit example. Yes, that's right.
What do you mean?
So in this case, in this case, I've written something down which has an h over an f1 and an f2, and a subset of the zeros of f1 and f2 go to 0 is, for example, putting tau2 to 0 and that combination to 0. And then I go in the neighborhood of where that happens, I compute the Jacobian, and I see what the residue looks like. Okay? And if I do that, I get an answer, which is not if I do that, I get the answer 1 over a. So it's really the legal definition. What this is really doing is what this is really doing is allowing you to enlarge into one object.
Why would I have gotten 1 over a without putting tau1 in the numerator and denominator?
Oh, because had you because
I would have said tau2,
well,
and then 1 over 8 tau.
So let me say it like this. So let's say you didn't know. Let's say you had a +1 there. Okay, right? Right. So, but you don't, of course. But if you had that and you thought that you were defining a residue by putting these factors to 0, you'd say, oh no, I'm going to get 0 because there's a tau1 upstairs. That residue is being killed. Actually, somewhere else it's not true. It's not being killed because there's some other factor somewhere else that you didn't think you're setting to 0 on your definition, which is going to 0. Okay. So,
I can see that.
Yeah.
If I have tau 1 upstairs and downstairs,
Right.
then I have to remember that it is something
That's right.
to be going to zero.
That's really all it is. Right. That's right.
I don't see why I have. You're saying that.
No, that is really
tau 1.
no. That is really all it is. What we're going to find is that is that there's some way of taking this object and actually multiplying by things upstairs and downstairs, so that I'm really multiplying by 1. But having multiplied by things upstairs and downstairs, I'm going to have enough structure so that all the residues, all the different residues that I need to define the contour, are included in the zero set of this enlarged denominator. That's all.
I guess what I don't understand in the example you gave.
Yes.
If I don't include tau 1 upstairs and downstairs,
Right.
the zero set is the point tau 2 equals 0 and tau 1 equals 0. Right?
Well, right. Right. So exactly.
And if I include it, it's bigger. You're saying it's tau 1 equals 0.
No, in this case, the zero sets are just tau 1 and tau 2 equals 0.
Separately or together?
Sorry?
Separately or together?
Both equal to 0 is the both of them equal to 0 is the zero set. Right. So I have
Of the denominator?
right.
The zero set is where the function vanishes.
The zero set is just where the function vanishes. That's right.
So-
That's right.
It's supposed to be like it's
No, I'm-
equals 0 or tau 2 equals 0 of the denominator. They're different zero sets. Whether I put the tau 1 downstairs.
That's right. That's right. So you get to choose a. You don't have to choose all of the zeros of the denominator. You have to choose some subset of the zero set of the denominator to define the contour. Okay. This will really be much clearer when you see an example. It's just. The point is that but the point is that you cannot do it just using these consecutive minors as they appear. There's no way of just manipulating these things and putting them together to make it happen. You have to start introducing other objects in order to glue everything together so that you can see this entire contour as the zero set of a single object. And that process actually has a physical interpretation. It has the physical interpretation of adding a particle, adding one particle at a time. So in order to actually introduce it, let me start with the simplest case. So I'm actually from the outset here introducing the idea of adding one particle at a time. Let me start with the simplest case where I start with the 5-particle amplitude, which doesn't require any contour, and I try to get the 6-particle amplitude. I'm going to get the 6-particle amplitude just by multiplying by the following funny object. Okay. So the 6-particle amplitude, remember, the denominator has all of these things except with a 456 and a 561. So I have to first of all get rid of the 512 here. Okay. Put a 561 downstairs. But I'm writing it in this funny, at the moment, funny-looking way. Okay. So I'm writing it as 1 over 561, 2, 3, 4, 4, 5, 1, 5, 1, 2, 1, 3, 5 over F6, which is 4, 5, 6, 6, 1, 2, 2, 3, 4, 1, 3, 5. Okay? Now, so this is a little bit funny, right? Because, for example, there's a 1, 3, 5 there and a 1, 3, 5 there. Okay? So, but again, I'm just insisting that the numerator is part of H and the denominator is part of F. Okay? I'm going to call this factor M6. So is it now clear? So if I just if I there's a 2, 3, 4 upstairs and downstairs, so I've done nothing. There's a 1, 3, 5 upstairs and downstairs, and then the 5, 1, 2 just gets rid of that guy. The 5, 6, 1 and the 6, 1, 2 complete the denominator. But now notice the zero set of F6 puts 4 to 0, 6 to 0, and 2 to 0. Okay? And that's my contour. Remember the even guys. In one presentation, I'm summing over the even guys. 2 equals 0, 4 equals 0, 6 equals 0. Okay? It also includes 1, 3, 5 equal to 0. That guy happens to have a 0 residue because it sits upstairs. But anyway, I have the zero set of this guy is just what I want. I'm writing it this way because this is going to be the way of thinking about it that generalizes to all cases. but also because this object has a beautiful interpretation. It turns out that if you evaluate this as a function of the external momenta, and now send the external momenta to 0, this factor m6 turns precisely into the soft factor. Okay? So there's no coincidence that I took the 5-particle amplitude, I multiplied by something to get the 6-particle amplitude. Well, that makes sense. The soft limit of particle 6 should land me on particle 5 with this famous universal factor. Okay? So what multiplying by m6 has done is like taking 1, 2, 3, 4, 5 and just adding 6 at the end. Okay? And so this funny operator that has 4 minors downstairs, this funny operator, 1 over f6, with the product of 4 minors downstairs, is developing a soft factor and is doing something. Okay? Products of 4 minors like this play a huge role in this business. Okay? And in fact, in a moment, we're going to see that first of all, in a moment, we're going to see that you can construct all the NMHV amplitude. In fact, all tree amplitudes can be constructed in this way. But secondly, we're going to see that deforming these functions is a very natural deformation of these functions that turns them from a single product of 4 minors into the difference between the product of 4 minors. And these operators, and these things thought of as operators, in other words, thought of as enforcing them as poles, going to their 0 set, is enforcing localization properties. It's enforcing localization properties in the Grassmannian that gives the object a particle interpretation and allows you to think of it as coming from the Twistor string. But we'll see that explicitly in a second. Okay. So we can keep going. If I take the 6-particle amplitude and I just multiply by m7, which is exactly the same as m6, but now I'm including particle 7, so I have to make room for it. And I do that just by shifting all the labels 4, 5, 6 over to 5, 6, 7. 1, 2, 3 stay fixed, then I shift everything over by 1. Okay? Now this is something more non-trivial than the first case. Remember, in the first case, we said it was a function of a single complex variable. Now we have that function of 2 complex variables that had an interesting contour with 6 terms. Okay? Now the 0 set of putting these things to 0 turns out to precisely give you that contour. Okay? It's a non-trivial exercise. The reason it's non-trivial is because you have all sorts of non-consecutive minors lying around here. Okay? And you can set some of these things to 0. It's not obvious ahead of time that setting these non-consecutive minors to 0 is going to end up giving you something that only picks out one of the residues of our original object that just puts these consecutive minors to 0. And the reason it happens has to do with various geometry problems. Like if you put 1, 2, 3 and 1, 2, 4 to 0, you happen to also put 1, 2, 3, 4 all on a line, which is the same as putting 1, 2, 3 and 2, 3, 4 to 0. So the solution to all sorts of geometry problems involving non-consecutive minors can be represented as solutions of putting certain bunches of consecutive minors to 0. But you can't glue them together without introducing these auxiliary objects. Okay? But gluing them together, introducing these auxiliary objects, is also precisely what allows you to map the bigger problem to a smaller problem by taking soft limits. Or conversely, to start from the smaller problem and grow particles, add particles, and get the full higher point amplitude from the lower one. So this particle interpretation, purely within the Grassmannian, this has nothing to do with space-time. It's really it's some manual way of showing how the higher point contours go into the lower contours, okay? By showing that they're actually part of some gigantic function, the 0 set of some gigantic function. And as I restrict myself to smaller and smaller pieces of it, I see the contour going down into the lower and lower point guys in a smooth way now. Okay?
Right this way, is the cyclicity manifest?
This way the cyclicity is not manifest, but the way the cyclicity becomes manifest is by going back to our original object. Right.
So it's not manifest at all, or
I'm going to make it manifest. One of the things that the Twistor string is going to make manifest is this. Okay, so right, but it also had it in its original form as well. So I'll tell you the various things that are made manifest in a second. So, but anyway, let me just say that this particle interpretation can easily be extended to all tree amplitudes, n squared mhv, n cubed, everything. What's remarkable about the tree amplitude contour then that we've seen is that what we colloquially referred to as a contour, which was really some sum of residues, okay, of this object with these simple cyclic bunch of minors downstairs, it can be sewn together into a legal contour of a bigger object with all sorts of non-consecutive crap upstairs and downstairs. But doing that allows you to get a one particle at a time interpretation purely within the Grassmannian. I keep emphasizing this because this is a particle interpretation not in space-time but in the Grassmannian. Now, what does any of this have to do with the Twistor string? Well, let me back up a second and start all over. Okay. We could have started back at the very, very beginning when we first thought about integrating over k-planes containing the lambda plane orthogonal to the lambda tilde plane. Okay? And remember, I told you at the very beginning, I could choose any measure here that I want. And as long as it had some GLK invariance. And we chose one that seemed nice, that had these product of the cyclic minors downstairs and so on. But all you really have to do is have it be GLK invariant and have it impose this many constraints. Okay? That's all it has to do. In other words, whatever it does, it somehow has to turn this into an integral over some lower dimensional subspace of the Grassmannian. A 2n minus 4 dimensional subspace of the Grassmannian with some function c of these variables sigma that label that subspace. 2n minus 4 just being the difference between that number of constraints and the dimensionality of the Grassmannian. So every theory in the Grassmannian, every Grassmannian theory is really just making a choice for what this subspace is. We just gave one of them that we liked, involving these consecutive minors, and what was nice about it is it allowed conformal and dual conformal invariance to be manifest at the same time. But you may have from the start wanted to do something else. You may have wanted to make some other interesting thing manifest. For example, you might have tried to make a particle interpretation manifest from the very start. What I mean by particle interpretation is normally when you have n particles, we think that they live in a space so that the configuration space is like n copies of some underlying space. So you could say that what I should try to do is take this 2n minus 4 dimensional subspace and think of it as being some underlying space to the n. Okay? That would give me a particle interpretation. So it would allow me to think like we normally do, that the configuration space is like n copies of something. Well, the minus 4 is a little annoying, but that's just a gauge redundancy. So if we go to very big N, this just tells us ahead of time what the dimensionality of sigma has got to be. It's got to be 2. So there's no choice for sigma but for sigma to be C2. Okay? So I have to have some maps from C2 from n copies of C2 into the Grassmannian. And, well, the minus 4 I can easily take care of by just some GL2 that I have acting on the C2. Okay, so I have a C2 with a GL2 acting on it, which I can equally well think of as a CP1 with an SL2 acting on it, which starts sounding more familiar. Okay? So I have a mapping from n copies of a C2 into the Grassmannian, or n copies of a CP1 into the Grassmannian modulo GL2 or SL2. Now, how do I do the mapping? Well, the obvious way that you'd want to give a particle interpretation is to say that I have this k-plane in n dimensions, but instead of thinking of it as k n vectors, which is the way it's presented, let me think of it as n k vectors. Okay? Sort of looks like a particle interpreter. I'm stacking a bunch of things beside each other, right? But I know that this has got to be labeled by a C2. So each one of these k vectors has to be canonically associated with some two-dimensional vector in C2. Fortunately, if you turn to page 5 of any undergraduate book on algebraic geometry, there's a completely canonical map that takes you from C2 to CK, or CP1 to CPK minus 1. And it's called the Veronese map. Okay? So if you take sigma 1, sigma 2 as coordinates on your C2, then what you do is you map it to all monomials in sigma 1 and sigma 2 with a power k. So in CP2 it would be sigma 1 squared, sigma 1, sigma 2, and sigma 2 squared. The point of doing that is that the GL2 that acts on this guy lifts into some particular GLK that acts on this guy. Okay? So that's good. The gauge symmetry over here maps into a some subset of the gauge symmetry that acts over there. So I can call this I'll put a sub V here to remind me that this is what I get from C2 by doing a Veronese map. And so now I've defined the subspace of the Grassmannian that I think has a particle-like interpretation. The subspace of the Grassmannian that has particle-like interpretation is labeled by some sigmas for particles 1 through n, and the following k by n matrix, where the columns are just the Veronese embedding, the Veronese map from C2 into CK. So this is what we should mean by something, by a point, something in the Grassmannian with a particle interpretation. Somehow I want to integrate over all these planes with a particle interpretation. If I want, that seems like a natural thing to do. What measure should I integrate with? Well, the measure should be GL2 invariant. And just like before we had GLK invariant measure, well, this is the simplest possible GL2 invariant measure you can use. So let's do what we did before. I'm going to integrate over the subspace of the Grassmannian with a particle interpretation with this measure. Okay. This object that we can call Tnk is nothing other than Witten's Twistor string theory for tree-level amplitudes. It's not written in the Twistor variables that Ed originally used. Ed worked in the Z Twistor variables, and these are the W Twistor variables. And you can trivially do the Fourier transform to take from W's to Z's. And when you do it, what you get is precisely the integral over the moduli space of all degree k-1 curves mapping a CP1 into CP3. But from this point of view, it's an integral over, it's just a rewriting, nothing other than a rewriting, but it's thought of instead as an integral over the subspace of the Grassmannian of this natural object that we like so much that allows a particle interpretation internally within the Grassmannian. Okay.
So did you actually show that this was the same as what you were doing before?
No. This is something else. This is, if you like, a set of words that you can, a set of Grassmannian words that you can say that would land you on what Ed did originally. Right. And now it's a very non-trivial fact that this is the same. Okay. So that's what I'm about to. That's what I'm saying. There's a kind of duality now. They're not the same integrand, and we'll see in a second. They're really not the same. But there's a Grassmannian duality that says that these two things are equal to each other. Okay.
And not by just changing the.
Absolutely not. You'll see what it is in a second.
You started out with an integral over C, and then you end up with an integral over sigma, right?
No. In this language, I'm not. You see, I just started all over again in this language. Okay?
Oh, so you don't have the integral over C.
No, I'm doing the integral over C. In fact, let me convert it to an integral over C. Okay. So this formula. This formula, you can trivially integrate if you like. You can trivially integrate in and think of this as an integral over C's just by putting in some delta function to enforce this constraint. Okay? So then that takes you back to the original Grassmannian form. Okay? And so you have something with some integral of some function of C. The function of C is nothing other than the integral of this thing with that measure. It's totally obvious. Okay? So this is something that in a particular gauge, Spradlin and Volovich and Peter Goddard and Louise Dolan did back in September, or maybe in August. Okay. But let me just write down the answer, not in a particular gauge, in a GLK invariant way. For example, you can think of the 6-particle amplitude. What you get by just doing the connected prescription for the Twistor string, which I should say is also associated with the Radu-Roigwan, Spradlin, and Volovich from 2004. But we're just translating that into the Grassmannian language. There's nothing, I mean, other than the realization that the connection exists, that this is just, there's nothing interesting here, okay? It's just translation. Now, let me in fact tell you some things. So what you get is the following. Remember, we have this integral over a single complex variable. What you get from the Twistor string is something that looks like this. From the connected prescription is something that looks like this. Beforehand, we had something that looks very much like that. Actually, the 135s cancel. Okay, so you're seeing some hint at the beginning of a connection. But let me tell you what this funny object is doing. We have a product of 4 minors here minus 4 minors. Okay, and I should have told you the contour here. The contour is to enforce all the poles of this guy, to sum over all the zeros of this guy. Now, what is this doing? Remember, I don't want to integrate over all k-planes. I want to integrate over k-planes that have this particle interpretation, which in this case means k-planes that look like, 1, sigma 1 squared, 1, sigma 2 squared, and so on. In other words, and I can think of that, not a random k-plane will look like that. Not a random 3-plane will look like that. In fact, if I have 5 particles, if I have any number of particles, this is the condition that those points lie on a conic in CP2. Okay? Any 5 particles lie on a conic in CP2. That's why there's no contour to pick for the 5-particle amplitude. However, when you have 6 particles, there is a single constraint for a 6th point to lie on that conic. Okay? This is the way of writing the single constraint for all 6 points to lie on a conic. A way of seeing why you have to have a product of 4 minors equals 4 minors is the following Star of David picture, which I'll just say very briefly. So if you put 1, 2, 3, 4, 5, 6, oops. There we go. Okay. Sorry, it's so messy. Okay. So I'm trying to figure out, does a C-plane have the form, I'm just taking out an overall scaling, does it have the form 1 sigma 1 squared, 1 sigma 2 squared, up to 1 sigma 6 squared? Can I put a 3x6 matrix into that form by a general GLK transformation? Okay. Well, the minors of this matrix are GLK invariants, or SLK invariants, but if something's going to equal 0, it'll be GLK invariant. So clearly, if I'm going to put in this form, there are going to be some relations between all the minors. In fact, this picture suggests what their relation can be. Every line, also notice that every submatrix here is just a van der Waals matrix, so the determinant is just the product of all the sigma I minus sigma j. Okay? So the determinant of any 3x3 block here is sigma 1 minus sigma 2, 2 minus 3, 3 minus 1. Now look at this picture. Every link in this picture, think of it as being a sigma I minus sigma j for whatever it connects. Okay? So this represents the product of a whole bunch of sigma I minus sigma j, which I can read in the following 2 ways. One way is I can read it like that. That triangle is the minor 1, 2, 3. Okay? This triangle is the minor 3, 4, 5. That triangle is the minor 5, 6, 1. And that final triangle is the minor 2, 4, 6. But the whole picture is cyclic. So this has to equal exactly the same thing, shoving everything over by 1. And so this single constraint, the difference between the product of 4 minors, the product of 4 minors minus 4 minors equals 0, is the single constraint that enforces that the 6 points are on a conic. It doesn't look like it, but this object is permutation invariant on all these labels up to a sign, as it should be. Okay? And the Grassmannian form of what you get from the connected prescription is littered with these objects, because it turns out that at any point, any k, k, any n, what enforces localization properties on things that have this, if you like, Veronese operators that test whether the k by n matrices can have a particle interpretation, always, always, always are products of things that look like this. Products of 4 minors. 4 minors minus 4 minors is equal to 0. You want to know the condition for 7 points to lie in a twisted cubic? It's 4 minors minus 4 minors equals 0. It's a collection of statements like that. Okay? And there's a simple proof of that. But that's why these objects are ubiquitous in this business. For any k. For any k. There's a simple argument for that, which I don't have time to explain right now. But and this, by the way, dovetails in very nicely with what Goddard and Dolan found. Goddard and Dolan gave an answer in a particular gauge for the entire thing. Okay? And what they found is that there were certain objects that kept making an appearance that were sextics. There were sextic polynomials in the particular gauge they were using is what we called the link representation before, which was exactly this canonical one where you set things to things that look like that. Okay? If you use this particular gauge, then these conditions turn into sextic conditions on the remaining C's. And they found that everything were always sextics. There's a very good reason for it, because there are always these products of a bunch of minors, and in this gauge they all turn into sextics. But geometrically, they're very clearly just enforcing these geometric conditions for points to lie on higher and higher degree curves. Okay. Now, in this very simple case of the 6-particle amplitude, in this very simple case, this does not explicitly look like what we get from the Grassmannian. But in this very simple case, it's easy to see a Cauchy theorem that proves the equivalence between the two of them. I should say, by the way, they're really, truly incredibly different. If you look at this object, it has, as a function of tau, it has 4 poles. It's a genuine quartic polynomial. It's a horrible thing. Each residue individually has no nice properties, just a truly horrible thing. In fact, this is the horrible object that RS and B ran into in 2004, and Mathematica summed the roots of these 4 quartics and ended up reproducing the tree amplitude. Okay, but each residue is some disgusting thing. Okay. Okay, now we can see why. So, and this is an exercise, I should say, again, not in this gauge invariant way, but in a gauge fixed form that both Spradlin-Dolovich and Goddard and Dolan did. Let's deform the contour off of this guy onto this guy. Now something nice happens. On these zeros, look, these things vanish. On these zeros, these things vanish, and the remaining thing is exactly our object. But on these zeros, 1, 3, and 5, which is exactly the contour for the 6-particle amplitude. Okay? So in this special case, it was easy to do a contour deformation. Now, you can write down the general form of this expression for any amplitude, and even for the 7-particle amplitude, it starts involving real gymnastics to use the global residue theorem to move contours around in order to prove that you end up getting to our object. And you do eventually, after like lots of work. You can think about it geometrically, and it's a lot less work, but it's still some work. Okay? And you have to be a little clever. You have to notice that these things lie in a plane, this, that, lots of cleverness as you go to higher and higher points, and it always works. But in fact, it's not because of cleverness. It's really because there's a more indirect argument that shows that you go from one to the other. Let's go back now. That was a detour, thinking about another way of thinking about the particle interpretation. Let's go back to our original object. Okay? We learned how to take our original object and sew it together into a nice legal contour. Okay? Now we can find that we can take this denominator and smoothly deform it so that at one end it's our object, and at the other end it's the connected prescription, or the Twistor string. I'll show you. Oops, except I did it wrong here. Okay? But it's like you take this object. The t should be on here, I apologize. Okay? And you just multiply that guy by t. Okay? If t equals 0, it's our object. If t equals 1, it's the connected prescription. Okay? But the residue should not change as you do this smooth deformation from one to the other. Okay? So in this case, it's trivial, but it really generalizes beautifully. So, I don't know if I showed you one of the explicit formulas, but remember this active multiplying by M6 and M7 had all sorts of terms in the numerator. There are lots of non-consecutive minors in the numerator and the denominator, and there's more and more of these non-consecutive minors upstairs. Okay, so you know what you're doing, but they're very definite expressions. But if you didn't know what you were doing, they would look quite complicated. In fact, they're not complicated. They're exactly just taking care of the soft limit, giving a particle interpretation, and all of that. But when you take those objects and you deform them in essentially the unique way that's possible, then at t equals 0 it's our object, and at t equals 1 it precisely turns into the connected prescription. That's why it looks like our object are like the quarks, because it's built out of these individual building blocks. The individual building blocks, all the symmetries are manifest. It's conformal, dual conformal invariant. Everything is nice. On the nice contour, in the NMHV case, on the thing that gives you this even odd interpretation, many things happen. On the one hand, you can blow them apart into space-time. On the other hand, you can sew them together into an object that, again, purely internally within the Grassmannian has a add one thing at a time interpretation, and then deform it to show very explicitly that it has a particle interpretation by connecting it to this Veronese map, which is what the Twistor string theory was doing. Okay? So it's a duality. It's not an equivalence. I mean, it's a duality in the sense that it's that they're not the same integrand. They're really different. They're different theories. They're different. But that's right. But they're continuously connected. In fact, I should say that there's really a sense in which you can push this analogy with the field theory duality further, and you can think of the amplitudes as being the partition function. So in other words, you start with this Veronese map picture or the connected prescription picture, and on the Grassmannian picture with a particular contour. And you do the integral with the measures as given, and that gives you an answer. But now you can start imagining computing quote-unquote correlation functions, where you multiply the integrands by various GLK invariant functions made out of the minors. The statement is that those objects are equivalent in the two theories as well. The fact that they're related, the fact that the equivalence goes through a contour deformation shows not just that the partition function or the amplitudes are the same, but that this whole set of correlation functions is also the same. Internal Grassmannian correlation functions, correlators of GLK invariants built out of ratios of minors, are equivalent on our Grassmannian formulation and the connected prescription formulation. What I'm saying is that the fact that these things are related by this deformation tells you more than just the amplitudes are the same. There's a lot of other objects that aren't amplitudes. We have no idea what they are. There are things that have internal Grassmannian interpretation, no space-time interpretation at all. But all of those things are equivalent to each other too. Okay? This gives some feeling that perhaps there's more life internally to the Grassmannian that's worth understanding more. All right, that's all I have to say. But I just want to end with what I think of as the most pressing question right now, which I hope we will address in the near future, which is, all this is very nice. It's nice that there's I think it's crucial psychologically that this object knows about loops. There's no conformal supergravity. There's no junk. It knows about honest loops. It knows about the leading singularities, but it knows about honest loops. It still leaves open the question: where are the actual? It knows about the tree, right? That's right. It knows about the trees and the loops. Exactly. It knows about the trees and the loops. But somehow it knows that there's something good about sewing things together in a way that looks like loops. Okay? But where's the actual honest loop information? Where are the infrared differences? Where are the polylogs? Okay? I told you we have this is a machine for generating algebraic functions that are Yangian invariants. We need transcendental functions too. Where are the polylogs? Okay? Where are the infrared differences? Where are the polylogs? And it's completely clear that is all tied up with this question. Okay? The Wilson loop in this story is clearly a fantastically beautiful object. It has amazing properties. There's been wonderful progress in computing it and understanding it by Juan, Davide, Gaiato, Fernando Alday, and others in the past, just quite recently. And it's mysteriously connected to all sorts of things. So there's clearly something remarkable about this object and very important about it, and it's invisible to what we're talking about so far. So somehow these two threads have to be brought into contact with each other, and that's really the next item on our agenda. There's something that might be much simpler and might have a much bigger payoff, which is to try to do all of this, even at tree level, for n equals a. And, well, there's many reasons, but which I don't have time to go into right now, that suggest that the n equals 8 story should be much more interesting. But perhaps the biggest one is what David keeps complaining about all the time, very rightly, that, it's a little silly to just talk about the S matrix for n equals 4 when it has all these other wonderful observables, but n equals 8 is all it's got. And so if anything morally deserves to have a nice theory for its S matrix, it's n equals 8. There's just sort of data obstacles right now to getting going. The data for even the simplest amplitudes in n equals 8 have not been presented and written down in the nicest way. And I think once we have the appropriate data, I think progress will be a lot faster. Sorry?
But given all this experience, you should be able to guess the answer. It is not a simple generalization of any of the things that we've done. That many things we've tried, but amongst other things, the fact that it's not conformal is very important, and but I'm completely I'll be willing to bet a lot that the story here is going to end up being much nicer even than it is for n equals 4. All right, thanks a lot. Yes.
So I know you hadn't talked about gravity, but do the KLT relations play any role in it?
I think KLT is going to end up being. I think KLT is not very important, and it's going to end up being. I mean, it's important. It's great. It's beautiful. But I don't think it's going to be. I think it's going to be seen to be one of many consequences of the right way of thinking about things, yeah.
So I guess just like the BCFW recursion.
Yeah. So BCFW also, in the end, I mean, it plays a huge role in motivating and thinking about things, but in the end, is like one representation of things, and it's not. That's what's interesting and non-trivial about this business is that we've had to learn to guess and introduce new kinds of redundancy. It's been a really good idea in physics to introduce new kinds of redundancy, but of course you never know how to do it until you figure out how to do it. Okay, and so that's really what's going on. The reason why BCFW was, in the end, the reason why we had all these different formulations and these different ways of writing the amplitude, you could say it's lots of different ways of gauge fixing the GLK, right? Right, exactly. But to do that, you have to discover that there was this extra redundancies. Yes.
At the very end, you introduced a new redundancy, which you're not explaining.
This deformation redundancy. Yeah, right. No, right. Yeah, we don't know what those. We don't have a deep understanding of those at all yet. Right.
And they're really equally redundant parameters.
Yeah, absolutely.
It's not a duality because you have this whole continuum.
Yes, no, absolutely. Yes, no, you're right. Calling it a duality is a misnomer. Absolutely. It's like
another redundancy.
It's really another redundancy. Right. I mean, it smells. There's a paper that, if I understood it better, I'm sure would shed a lot of light on this, which is the only other place in the physics literature that the global residue theorem was used, and it was in fact explained, if I could understand it, was Ed's paper with Chris Beasley. So Ed had this paper with Chris Beasley from 2003, where they used the global residue theorem to show that a certain instanton sum that had to vanish from some space-time point of view vanished from a worldsheet point of view. Okay, and there was some miraculous identity that had to be true that they found was the global residue theorem. But then they proved the global residue theorem from some supersymmetric quantum mechanics argument. Okay, and so if I could understand that proof, but it would probably be helpful. The thing is that we need a much more refined version of it, because what we're talking about here is the equivalence of something on one contour and another contour. It's not just blindly summing over all residues to getting 0. It's another interesting kind of equivalence. But I suspect since we now turned it into, and that was the progress in realizing that there was this continuous deformation, because what we were doing before then, and what our friends before were doing, was just doing these very discrete, choppy things of like taking a contour and moving it there, and then shoving things around, and you have to do lots and lots of change of these things till you prove the equivalence. But when you see that they're smoothly connected, it's a much more straightforward argument. But there's got to be some way of actually proving that. Right.
But then the Joshua would like
to exploit it. Yeah, right. I don't know what it means.
Once you do that deformation, it doesn't, away from t equals 0, 1 doesn't have a nice geometric form.
No. Somehow, right at t equals 0, it has a nice geometric interpretation, k-planes and n dimensions and all that stuff. At t equals 1, it has a nice geometric interpretation, Veronese embedding, particle interpretation, Twistor string, and so on. Who knows what it means in the middle, right?
Yes. Something the GLK symmetry. So you say that that's related to the gauge symmetries of the gauge field, but the gauge symmetry is space-time dependent. What's the GLK?
Oh no. I mean when I say gauge symmetry, I really mean redundancy. I mean, it's just a new kind of redundancy. I
think this has nothing to do with.
No, it has nothing to do with the space-time gauge symmetry, of course. No.
I mean, on the topic of the space-time, so if you go back and look at your, integral over C with the minor smooth denominator,
yes,
the only place where even space-time dimension appears is in the delta function.
That's right. Right. So the delta function is giving a little window of space-time peeking into the Grassmannian. Right. Right.
So then, to continue on this, if you change dimension, what changes is the lambdas that you have are vectors.
Everything changes when you change dimension, because this entire picture of momenta being lambda tilde, and all of that completely changes.
So that's what I'm having trouble seeing. In terms of just the Grassmannian that you have there.
In terms of the Grassmannian, you could easily have things that aren't 2 planes. You could have 3 planes, all sorts of other planes. But then the Lorentz symmetry would be SL3 cross SL3. Right. It's not a Lorentz group. Yeah. So that much is very, very special to 4 dimensions.
Okay.